All right, so thank you, Laurent, for the introduction, and thanks for organizing this wonderful webinar. It's a great opportunity to stay in touch with the French community in these uncertain times. In this talk titled Intelligent Imaging and Reverberation-Coded Apertures, I'll talk about two of our recent projects in collaboration with our colleagues in Paris, but also United States and China, that we're very excited about, and we hope that they'll also be of interest to some of the people in the audience from the computational imaging community. So computational imaging, as I'm sure most of you are aware, and Mathieu just gave a pretty broad introduction, essentially consists in illuminating the scene with a series of crazy patterns and then figuring out what the scene must have been based on the reflections. And there's been a lot of implementations of computational imaging over the past few years. Here, since we're kind of in this French setting, I picked a Thomas seminal paper on top, where essentially he used a chaotic cavity in order to multiplex the spatial scene information across spectral degrees of freedom. And there has been follow-up work where people use, for example, configurational degrees of freedom by endowing a chaotic cavity with programmability. The key point here is that the degrees of freedom of a complex medium play the role of a coded aperture in computational imaging. And in this talk, I would like to address two aspects that I believe are important to pretty much any application of computational imaging. The first one is latency. So I will show you how by intelligently choosing the illumination modes, you can remarkably improve the latency. And the second topic that I will address is resolution. First of all, to show you that the resolution is not limited by the wavelength, and then more importantly, actually to introduce this concept of reverberation-coded aperture, which looks very much like a Thomas setup on here, except that the scene is inside the chaotic cavity. And I'll explain to you in terms of the physics why this tiny difference actually has a huge impact on the achievable resolution. So let's get started with the latency. So most practical applications of computational imaging face latency problems. That's why a lot of the time, the ideas that have been developed in labs have not actually found their way into the real world yet. So for example, if you think about security imaging, ideally you would like to be able to do the imaging without having people to stop in front of the imager. In autonomous driving, of course, the car has to make decisions within milliseconds if it should brake or not. And in touchless human-machine interaction, essentially the gesture recognition should be run on a smooth basis. Now, in order to understand how we can tackle the latency problem, it is actually very useful to realize that whenever we conduct computational imaging, almost always the ultimate goal is not to just create an image that is visually appealing, but to actually answer a specific task. So in the first case here, the specific task could be, is the person carrying a concealed weapon? In the second example, the task could be, is there a pedestrian on the road ahead? And in the third case, the question could be, what gesture is being displayed in the scene? And so with respect to that specific task, we can classify information into relevant and irrelevant. Now, if we look at a sort of traditional sensing pipeline, what we see is that we drag irrelevant information all the way from the scene through the measurement into the image. And only at the very last stage, we actually discriminate between relevant and irrelevant in order to answer the specific task, which is why we're doing all of this in the first place. So ideally, what we would be doing is discriminate already at the data acquisition moment between relevant and irrelevant, so that we only acquire relevant information. And then we can actually skip the imaging step because we can directly answer the task that we're trying to answer. And you notice that only acquiring relevant information actually has a double advantage. So first of all, each measurement contains more useful information, which means that you need fewer measurements. And if you have fewer measurements, you also have less data that you have to process. So let's see how we can implement this. So the first step where you map the scene to the measurement happens on the physical layer through wave propagation. And in order to actually somehow control the illumination modes of the scene, and in order to implement everything about intelligent imaging that I'll talk about, you need a reconfigurable data acquisition. So a common way to achieve that is to have programmable meta-atoms that are integrated into the hardware that you're using, such as dynamic metasurface transceivers, programmable reflect ray metasurfaces, something like this. So this means that on the physical layer, you have trainable physical weights. And then once you've obtained the measurement, you analyze the measurement to answer a specific task using, for example, an artificial neural network, which is a trainable data processing step. And again, you have trainable weights, but this time they're of digital nature. And the whole idea of achieving intelligent imaging is to look at this pipeline in an end-to-end fashion from the start to the end. So that means we have both physical and digital weights. Now, in order to implement this in practice, we actually need a model to describe what happens on the physical layer. So we need a forward model. And there are different ways to do that. Two important categories in which you could do that is, first of all, analytical forward models. So for example, if you're using dynamic metasurface transceivers, you can often approximate meta-atoms as dipoles and then come up with a coupled dipole formalism that accurately predicts the forward model. In other cases, so here's an example of a programmable reflect ray metasurface, it might be more difficult to write down analytical descriptions. And so you can just train another neural network that will approximate the physical forward model. Either way, once you have a forward model, you can integrate it into the learned sensing pipeline. And what you can see here is a schematic drawing of what that would look like. So the scene is illuminated by a wave, and the scattered wave interacts, first of all, with the physical layer, which consists of those programmable meta-atoms, which are physical trainable weights. It might also scatter through some chaotic cavity or similar. And then the information smoothly continues into the digital layer, where again, it scatters through the digital nodes of the neural network. And finally, it outputs the answer to the specific task. So in this case, what gesture is being displayed. So you notice that you have both physical and digital layers in one pipeline. You have correspondingly both physical and digital weights. And then you can jointly train both of them using standard techniques such as error backpropagation. Now in practice, often you have to be actually a little careful because the physical weights are typically binary. So it's 1-bit coding, it's a 0 or a 1, which can pose some problems for error backpropagation, but there are ways to work around that. So let's see some examples of this learned sensing technique. So on top is a numerical study where we have a dynamic metasurface transceiver illuminating a scene that contains a metallic number, and then the reflection is captured by another dynamic metasurface transceiver. And the task is to recognize the metallic number. And so here we're plotting as a function of the number of allowed scene illuminations, the achievable classification accuracy of the number in the scene. So the purple line is what we achieve with our learned sensing approach. And we're comparing that to 3 state-of-the-art approaches. So the first one is random illuminations in blue. So that would correspond to, for example, using the frequency diversity of a chaotic cavity. The red one is orthogonal scene illuminations. So you try to make sure that you're illuminating the scene with patterns that do not overlap at all in order to reduce redundancy in subsequent measurements. And the third, the yellow benchmark, is the idea to illuminate the scene with principal scene components. Now, as you can see, there's a significant improvement if you use learned sensing, especially when the number of illumination patterns is limited. And that is exactly what translates into this remarkable latency improvement if you intelligently illuminate the scene. And we also studied this idea in experiments. So here we're using a programmable reflect ray metasurface in order to illuminate the scene. And we're trying to recognize human gestures. And again, as you can see, qualitatively the same trends as above are observed. So that concludes the first part of my talk on latency. And now I want to focus on resolution and try to understand if there is a fundamental limit to resolution in computational imaging, and how we can possibly bend it. Now, there's a lot of misconceptions about the resolution, most of which are driven by the idea that it should somehow be related to your ability to focus electromagnetic energy. And of course, the free space focusing is limited by the diffraction limit. But computational imaging is actually not based on focusing, because as you saw previously, it's all about multiplexing information. And secondly, all of these arguments actually do not even take into account the availability of a priori knowledge, which is very common, especially in these days based on artificial intelligence. There's also another sort of argument which says if you're not using evanescent waves, then you shouldn't be able to access sub-wavelength information. But I'll show you that this is in fact not true. And so here's the general idea. So on top is just the very traditional coded aperture scheme, where you have a source that illuminates an object and the scattered wavefront is multiplexed across multiple configurations of coded aperture onto a single detector. Now, we've seen, for example, in Mathieu's talk, a lot of implementations where you use the degrees of freedom of a complex scattering medium to replace the coded aperture. So you can do exactly the same trick using a complex medium. Now, what I want to focus on now is what we call a reverberation coded aperture, which looks very similar to the second case, except for the tiny difference that wave source and object are inside the complex scattering medium. And that tiny difference actually has a huge impact on resolution. And the reason for that is that in the second case, the wave interacts only once with the object, whereas here in the reverberation coded aperture, the wave interacts with the object countless times. In fact, the number of times that the wave interacts with the object directly depends on the reverberation time or on the dwell time of the wave in the medium. And what you'll see in the subsequent results is that the longer the dwell time, the higher is the achievable resolution. So I'll demonstrate these ideas to you for a prototypical localization problem. So trying to figure out the localization, the position of an object. And you can think of this as essentially being a very simple imaging problem. So this is the general localization problem that we're dealing with. So you can see a metallic complex scattering enclosure that acts as the chaotic cavity. We have two antennas here between which we measure the transmission. And here are the metallic objects that are outside the line of sight of these two antennas that we would like to localize. And so we can use, for example, spectral degrees of freedom. We also have programmable metasurface here, so we can also use a series of random metasurface configurations in order to use configurational degrees of freedom. Either way, the problem, if you think about it in terms of information flow, is that you have an information, the location of the object, that is encoded in a measurement through wave propagation on the physical layer, and you do the multiplexing, for example, using different configurations of the metasurface. And then the digital processing layer has to kind of undo what happened on the physical layer. So you try to approximate an inverse function of the physical layer. The information is, of course, very scrambled here. So that's why in the following actually use a neural network to do this data analysis part. So here, what I'm showing you is on the left, the dwell time of the waves in the system, and on the right, the achievable resolution. So my whole argument is that the parameter on the left, the dwell time, drives the achievable resolution, so the parameter on the right. In order to explain that, we're looking at three representative cases. The first one is free space. The second one is a chaotic cavity with a medium quality factor. And the third one is a chaotic cavity with a high quality factor. So they correspond to three distinct dwell times. And as you can see already, if you look at the left and the right figure, the higher the dwell time, the lower is the localization error. And in fact, we identified three distinct mechanisms through which the dwell time positively impacts the localization error. The first one is pretty obvious. It's that essentially the longer the wave lives in the system, the more signal you measure, and so the better is your signal to noise ratio. The second mechanism is still pretty obvious, and essentially it's about the redundancy of subsequent measurements, because the larger your dwell time, the less redundancy you have. And that is true if you use spectral degrees of freedom, but also if you use configurational degrees of freedom. But the third and probably most interesting of these three effects is the fundamental sensitivity of the wave field to perturbations. And that sensitivity is directly related to the dwell time. So you can see here the parametric derivative with respect to the position of the object. And you can see how these distributions, for example, in terms of the mean value, clearly correlate with the dwell time. Now, I told you that these three factors all independently contribute to improving the localization error. And in order to evidence that more clearly, I'll focus in the following just on the third and most interesting factor by eliminating the other two. So how can we eliminate them? Well, we can fix the signal to noise ratio, and we can just use a single measurement, and that way we don't have to worry about redundancy in subsequent measurements, and we'll be left only with the contribution of this third effect. And this is what we did here. So for a single degree of freedom, as a function of the signal to noise ratio, you can see that the higher the dwell time is, so here given in terms of the quality factor, the lower is the localization error. And we also tested this idea in experiments. So we're using, again, similar to the image I just showed you, a metallic complex scattering enclosure. We have a small programmable metasurface therein. We do the measurements using a software-defined radio. And we observe localization errors as low as 1/76th of the wavelength. So with that, I'd like to wrap up. So in the first part of this talk, I introduced the idea of intelligent imaging, where you have a task-aware physical layer that allows you to drastically improve the latency. And in the second talk, I introduced the idea of reverberation-coded apertures, where the dwell time dictates the precision, and that is what allows you to achieve deeply sub-wavelength resolution without any use of evanescent waves. So I hope some of you will find the two ideas related to latency and resolution useful for your own work on computational imaging. And I hope soon we'll all be able to meet again in person.
Okay, thank you very much, Philippe, for your very interesting presentation. Don't know if we have some questions. There might be some. Not for the moment. I may have one. We know that the reverberation time or the dwell time you mean is related, if I am not wrong, to the ratio between the size of the cavity you're using and the wavelength. Is it true?
Yes, yes. That is one. I mean, attenuation is another important factor.
Okay. And do you know techniques, or maybe you presented it and I didn't catch these points? Do you know techniques that could be used to increase the dwell time values with a given volume?
Well, in that case, I guess you would have to minimize either the attenuation or the leakage of radiation from your enclosure.
Okay. And what is the role in the cavity of the moving? You have a turntable inside.
Yes.
What is the exact role of this turntable inside your box?
In this proof of principle experiment, we're trying to determine the position of this small sub-wavelength object, and that object is constrained to moving along a circle. So it's sort of a one-dimensional localization problem.
Okay.
And we're doing this with, so here's one antenna, here's the other antenna. So we're not using evanescent waves or anything. We're doing this kind of from far away, not within the line of sight of the object. And what we show is that you can determine this position of the object with precision, something like λ/76, just thanks to the dwell time. And if you reduce the dwell time, for example, in the experiment, what we did, we just opened the top cover of the cavity, then that causes a lot of leakage of radiation. So you have lower dwell time, and you can see how the localization accuracy drastically deteriorates.
Okay, so it may be okay for those of us who studied the digital communication, there might be this relationship between time and bandwidth, like the correlation time in when you talk about a communication channel. All right, there is one question from Thomas. I can try to translate it. Is there any approach able to determine the location of an object in a cavity without having to characterize the response of this cavity for each position?
Well, no, I think that's kind of the price that you pay, because you're using the chaoticity to encode the information, but because it's chaotic, you have to somehow characterize it. I mean, it might be possible to find somehow simpler ways to characterize it than the ones that we use, but I think you can't get around the characterization step.
Maybe to go in this direction, do you think that you could use some kind of auto-focusing techniques, similar to those that are used in synthetic aperture radar, to using a kind of contrast, if you put one object and if you want to characterize a single object, then the response, the well-focused response of this object should be very sharp?
Well, the problem is that we're not actually doing any sort of focusing here. So, okay. I mean, it's all multiplex measurements. Never is energy focused anywhere.
Okay.
That's why I'm not sure this can be directly applied.
Don't know if we have.
Oui, j'avais une question. Vous m'entendez?
Ah oui, oui, très bien.
Oui, bonjour. J'avais une question par rapport à la présentation de Mathieu. Sur un moment, Mathieu, tu parles de ISAR et j'ai pas très bien compris ce qu'apportait l'approche computationnelle, parce que dans ce contexte-là, il y a besoin que d'une antenne. La diversité, elle est créée par le déplacement de la cible.
Alors, je sais pas, on a peut-être perdu Mathieu.
Il est parti.
C'est perdu en route dans le couloir. Je peux peut-être répondre à sa place. En fait, c'est une approche d'imagerie ISAR 3D proposée par des collègues de Pise, Marco Martorella, qui utilisent en fait 3 antennes en L qui permettent de. Alors, l'antenne, le couple en élévation permet de localiser un diffuseur en élévation par interférométrie. Et le couple en azimut permet quand on fait de l'image ISAR, en fait, avec une seule antenne, on arrive à focaliser, mais on a un problème d'échelle. Le passage du Doppler, le passage de Doppler en mètres suppose qu'on ait une référence ou un a priori sur la scène. Et avec ces antennes-là, on peut passer à l'échelle, avec les antennes en azimut, on peut passer à l'échelle facilement, avec une simple équation.
D'accord, merci.
Voilà. Ouais.